Welcome to my course on digital signal processing. So when people ask me what signal processing is, sometimes I respond by saying it's about processing signals. And you may think I'm just trying to be funny when I say that, and I am partly trying to be funny, but that really is true if we understand what is a signal and what I mean by processing of a signal. So let's answer the first question first. So in general, signals are just time-indexed sets of values. So we have a collection of values taken at fixed points in time, maybe every second, every tenth of a second, maybe 1,000 times a second at a fixed distance between those time values. But it's a set of values, and so if I plotted those, the x-axis would represent the point in time, and the y-axis would be the value of whatever we're measuring at that point in time. In many cases, the signals represent some type of physical phenomenon. And in fact, many of these you would already be familiar with. We can record sound. So a collection of sound values, we measure those by changes in air pressure, that would be considered a signal. We can record temperature values. And if we collect those together, those are a signal. You're probably familiar with brain waves and heartbeats. Each of those is a signal. But there are some less obvious examples. Stock prices are signals because we collect prices over time. And so if I plot those, the x-axis is the time of a price, and then the y value is the price at that time. Images are considered signals. Now, the way that images are considered signals is slightly different than what I've described here, because not only are they two-dimensional, whereas each of these is one-dimensional, and stock prices would be considered one-dimensional as well. But not only are these two-dimensional, but they're indexed by position. So instead of finding them at a given time, you find the value at a given XY coordinate. And then you have a particular combination of colors if you're talking about a three-dimensional color value at that point on the image. What does it mean to process a signal? When we process a signal, we're really just taking in the signal and then making changes to the signal or doing something with it to produce a new sequence of output values. So an example of that is to produce the moving average for stock prices. This is something that investors sometimes do, and the purpose is to smooth out the fluctuations in the stock price so it's easier to see the overall trend of the price. So let's see that in action. So my blue line here is the daily closing price for some stock. And so if we look at it, we notice that it seems to be going up right here, then it drops down, then it goes up, then comes down, up, down, up, down, up, down. Well, it's going back and forth. And of course, these are daily values, but if I were to look on a minute-by-minute basis or hour-by-hour basis or something like that, I would also see that it fluctuates a lot. The problem with that is that if you're looking at it, it's hard to know what in general it's doing because it's going up, it's going down, going up, going down. As an investor, you probably care about the overall trends. You want to know, in general, does it appear to be going up? And in general, does it appear to be going down? So my orange line here is a 10-day moving average. And the way I calculate that is I take the first 10 values. So this would be values 1 through 10. And I calculate the average of those. Then I take values 2 through 11 and calculate the average. Then I take 3 through 12 and calculate the average. And when I plot those, I get the orange line here. So we can see that in general, it's going up right here, then it drops, then it goes up for, I guess this is about day, say 35 to day, we'll call that 60 or something like that. So about from days 35 to 60, it's going up, then it levels off a little bit, then it goes up some more, levels off, goes up some more, and so forth. But we see that the orange line is smoother than the blue line, which makes it easier to see in what direction the price is moving. So what are some other examples of processing? Sometimes we want to model a signal in order to understand it. So one of the most important tasks in signal processing is to take a complicated signal, like what we saw here, say the blue line, and to decompose it into simpler things, in particular sines or cosine waves. So for example, we might have a signal and we realize that the way it was produced is to take a 5 hertz sine wave and add it to a 20 hertz sine wave. Hertz just means cycles per second. So that means if this was 1 second, the 5 hertz signal is doing this, goes up and down 5 times completely in 1 second, and the 20 hertz one is cycling faster in that 1 second. And so what happens is you add the corresponding time values, or the corresponding values in time, at time 0 seconds, 1 second, 2 seconds, or so forth. Add those together and you get a more complicated signal. Another common task is to filter signals. Now the term filter is used a lot in signal processing. In many cases we use it the same way I use in English, which is to filter out or remove something. That's technically what happened here. The orange line is the result of applying what's called a low-pass filter, because that's what a 10-day average is, a moving average. It's a low-pass filter. So it filters out those components that fluctuate very quickly, leaving only the things that fluctuate more slowly. So I did filter out something. But just realize that the term filter in signal processing actually can have a more general meaning. In general, it's really about making changes to the signal. So if I were to have a system or a filter in which a signal came in and I simply doubled the amplitude of every value, I'm still applying a filter, but I'm not technically removing anything. So we're not always restricted to that definition, even though that is one of the most common ways signal processing is used. Another way signal processing is used is to find patterns in signals, possibly with the expectation of making predictions. Signals are used in finance, but there they typically call them time series. And the holy grail of time series analysis is to predict future stock prices, for example. If you knew how to do that with a high degree of probability, you would get rich. So lots of people want to do that and attempt to do that, but I guess they're keeping a big secret as to how well they've actually done. So there's lots of applications of signal processing, and we'll see many specific applications throughout this course. Now, when people discuss signals, they often divide them into 1 to 2 categories: analog signals and digital signals. Generally speaking, analog is referred to or is used to describe, say, real-world signals, like recording somebody's voice. And it's really about things with continuous values. Whereas digital signals are things that have been discretized and probably stored on my computer or transmitted over a network cable or something like that. Now remember that many signals are really a time index sets of values. So we have 2 axes when I plot those, the x-axis and the y-axis. And so strictly speaking, the amplitude, which is the y-axis, could have continuous values or it could have discrete values. And the x-axis, which represents time, could have continuous values or discrete values. So the combination of those actually leads to 4 combinations. So let's see those. So the 2 plots at the top have analog amplitudes, which means that it's continuous in nature. And so that means that if I take any 2 amplitudes here that are of different values, there's an infinite number of potential values between them. All right? And then if we look at the time component, if I pick any 2 times that are different times, there's an infinite number of time components between those. So this is continuous, this is continuous. And this is an image of my voice being recorded. Over here I've taken some temperature values and plotted those. Now the line that you see that's moving through here is the actual temperature values, and it's continuous in nature. So between 79 degrees and 76 degrees, there's actually an infinite number of different levels of precision. But I've taken temperature values every hour. So maybe this is midnight, and maybe that's like 75.83 degrees, and at 1 a.m. maybe that's 79.06 degrees, and at 2 a.m. maybe that's 77.03456 degrees, and so forth. So I've taken the temperatures at discrete time values, but the range of potential temperatures is still continuous in nature. These 2 plots have digital or continuous amplitudes. This represents traffic signal values. at least in the United States, traffic signals are represented by a green light, a yellow light, and a red light. But whenever we have a particular light, it's that same color for a continuous amount of time. So maybe for one continuous minute, it's green, and then it shifts to yellow, and maybe it's yellow for 15 seconds or something, and it shifts to red, and I guess that would mean it's red for a minute plus 15 seconds continuously, and then it shifts back to green and repeats. So we can see there's 3 distinct or discrete values, but each one is represented by a continuous time interval. And then our last image here has discrete or digital amplitudes and discrete time values. And this represents roll of a die or one of a pair of dice. And this is what we call a stem plot. The actual values are the little circles at the top. So if I roll a 6-sided die, maybe the first time I get a 3, then I get a 1, then I get a 5, then I get another 1, and so forth. And so we can see this is discrete and this is discrete. Now keep in mind that regardless of which of these situations we're talking about in the real world, once I've taken something and discretized it so I can store it on my computer, it's technically in this category. Even for voices, if I record voice and I want to store it as a collection of bits in a music file, it's really in this category because I take samples at predetermined time intervals, maybe 20,000 samples per second. And then each of the amplitude values has to be rounded off to some degree of precision. And so that means this is discretized and this is discretized. And so it's really in this category. So how do we do that? How do we go from this real world situation to this situation right here? Well, it's what we have right here. So this is 1/2 of a sine wave. So at the top, I have my original signal. We assume it's continuous in time and continuous in amplitude. And then what I do here is I've taken these samples and I've sampled it such that I have 4 samples. That's the red dots. 4 samples for every 1/10 of a second. But what happens here is like this right here. I've chosen to sample at time 0, and the value on the blue line really is 0 at that point. But then when I sample at this point, I go up to the blue line. I chose to round these values off to 1/10 to make it more obvious that I'm not on the line. And that's called quantization. This rounding of the amplitudes to some degree of precision is quantizing the values. So maybe what I really have here on the blue line is 0.198764. But rounded to the nearest 10th, that's really 0.2. And then this value here, maybe it's really 0.30605, but rounded to the nearest 10th is 0.3. And so I do this at each value. Notice here, all 5 of these values get rounded to 1. The middle value truly is 1 because that's what a sine wave would be at this point in time. But the other 4, 2 on this side and 2 on this side, have been rounded off to 1.0. So that's how we do that. So what's next? I consider my version of signal processing to be less theoretical and more conceptual than what you would get in the typical university level course. But I think you still have to deal with numbers to some degree. And one reason for that is I think it aids in understanding. Otherwise, it's just magic. You're pressing buttons on a computer and not really understanding why things work the way they do. Now, the numbers that you deal with in signal processing often include complex numbers and also complex exponentials. And in fact, lots of the theory is described in terms of complex exponentials. So I'm going to review that in an upcoming video. Another thing I'm going to do is make a collection of videos that give you a quick overview of Python. Now, if we go back and look at these plots, this plot and this plot, each of these 4 plots, this plot, every one of those I produced using Python. And one of the things I like about Python is it lets you do a lot without a lot of work. And I think that the pictures really aid in your understanding. Imagine I was just trying to describe a moving average to somebody who didn't know what a moving average was. Maybe you understand what it is, maybe you don't. but would your understanding have been the same as what I hope you got out of looking at this picture? I think this is much more clear than giving you a set of numbers and trying to explain what would happen to those numbers. And so Python lets us quickly do things to see how things work. And that's what I like about this course. And then also, I'm going to actually implement some signal processing techniques to do things. For example, remove noise from images or remove noise from audio files. And Python makes both of those extremely simple. Now, there are things that would be too difficult for us to do, but we won't get into that. Now, if you're already familiar with these, you can skip those videos and move on to the next actual signal processing video.